Hello, my name is Shahriari, and this is a lecture in a series of lectures on elementary mathematics. The subject of this lecture is basic counting, and in particular, what's called the multiplication principle. Here's three problems that we will do in this lecture. How many odd five-digit numbers with exactly one of the digits equal to 4? So you want to count that. How many five-digit numbers can you count that are odd numbers and exactly one of their digits is 4? How many odd five-digit numbers can you find with all distinct digits? You roll three normal dice. What is the probability that you will get exactly 1/6? What's the probability that you will get 3 6s? These are some of the questions that we will answer. Let me just tell you what the multiplication principle is. It's a very straightforward principle, and it's not even clear that it will have much use, but we use it quite often. What it says is that if you want to choose two items, and if it happens that you have m choices for the first item, and if also happens that regardless of what you choose, you have n choices for the second item, the n choices are not dependent on which choice you made for the first one, then in total, for choosing the two items, you will have m times n, mn choices. For example, let's say that you want to pick two toppings for your pizza, one of them a meat topping, the other one a cheese topping. For meat, you have three choices: chicken, pepperoni, and sausage. For cheese, you have four choices: pepper jack, mozzarella, cheddar, and provolone. How many choices altogether you have for toppings? Three choices for meats, and regardless of which ones, you have four choices for cheeses, and so 3 times 4, 12 possibilities. You could do chicken, pepper jack, chicken mozzarella, chicken cheddar, chicken provolone, that's 4. You can do pepperoni, pepper jack, pepperoni, mozzarella, pepperoni cheddar, pepperoni provolone, that's another 4, and another 4 for sausage. That gives you 3 times 4, 12. Again, a very straightforward rule. Just repeating, this is one way to visualize it. You've got a fork in the road with m possibilities, but then if you follow any of those, then regardless of that choice, they have n choices for the second time you come to a fork. Altogether, how many paths do you have? It's going to be m times n. You have m first choices. For each of them, you have n choices. The total is m times n. Another example, British Columbia license plates for consular officials are all of the form XX, A, B, C, L. And what are these things? XL stands for either CC, HC, CS, or SR. CC is for consular officers. HC is for honorary consuls. CS for administrative staff or technical staff. SR is for sub-state foreign officials. So XX could be one of those four things. And A, B, C are 3 digits. So A could be 5, B could be 0, C could be 9. It's a 3-digit number there. And L is a letter, except they don't use I, O, Q, U, Y, or Z. They don't use I because it gets confused with 1. They don't use O because it can get confused with 0, Q with O or 0, U with V, and Y and Z actually the rest of Canada does use, but British Columbia doesn't like that, and they do not use Y and Z. So the question is that how many such license plates can you make? How many choices do we have for XX? We have 4 choices. The choices we have for A or for B or for C does not depend on that choice. And we have 10 choices for A, the 10 digits, 0 through 9, and 10 choices for B, 10 choices for C. And we have 20 choices for L because 26 letters. 6 of them we're not using, and none of these choices depend on the one before. They're independent of each other. The total number of possibilities by the multiplication principle is 4 times 10 times 10 times 10 times 20, which is 80,000. This time I use the multiplication principle for more than 2 tasks, but it's the same thing. Now let's switch to probability. Finite probability is another name for counting. You're just formulating it a little bit differently. Intuitively, probability of an event is a measure of the likelihood of the event happening. But there are many different ways of thinking about probability. There's subjective probability, there's axiomatic probability, and here we're going to assume a finite number of equally likely outcomes. In fact, that intuition about probability being a measure of likelihood of things happening depends on things being finite. Here we have finite number of possibilities, and each of them is equally likely to happen, pretty straightforward, and that's where we want to define probability. Probability is always a ratio. In the denominator, we have the total number of possibilities. How many possibilities are there in total? In the numerator, we'll put from among those possibilities, how many of them are the ones that we want to count? How many of them are the ones that are favorable, are the one that we want to count? And with that ratio is the probability. If you want to say that a little bit more precisely, then you need certain words, vocabulary: experiment, sample space, event, and probability. Experiment is a clearly defined procedure that produces one of a given set of outcomes. And sample space is the collection of all of those outcomes, is the set of all the outcomes of that experiment. An event is a subset of the sample sample space. And again, our assumption is that we have a finite sample space, or the possibilities are finite, and the outcomes are equally likely. If S is the finite sample space of equally likely outcomes, and E is an event, then the notation for the probability of E is PRE. That's the one I use, probability of E. And it's a ratio again. When we put absolute value signs, we mean the size of the set. Again, it's a ratio. At the bottom is the size of the sample space. That's all the possibilities. And on the top is the size of the event, the number of favorable outcomes, the ones that we are interested in their probability. And probability is the ratio, is what percentage of the total sample space is occupied by our event. Let's look at a simple example. What's the probability of even number of heads in 3 tosses of a coin? What's the experiment? The experiment is that we're tossing 3 fair coins. And the sample space has a whole lot of things to it, but one of them is HHH. You might get 3 heads, or HHT, head, head, tail, and so forth. So the way to think of it is that you have the set of these results of this experiment, the outcomes of the experiment. And an event here is going to be those elements of the sample space where the number of heads is even. It would be things like HHT and HTH, where they have 2 heads. And so that event is a subset of the sample space. For example, TTT, that has 0 heads, and that's an even number, and therefore that's in the event space. Now, what's the probability of E? We would have to count. So first of all, what's the size of the sample space? We use the multiplication principle. I have 2 choices for the first toss of coin, head or tail, 2 choices for the second one, and that's independent of the first one, and the same for the last one. And therefore, the number of possibilities, the size of the sample space, is 2 times 2 times 2, 8. And what about the event? The event is how many of these 8 have even number of heads. One of them is just when you have no heads, 0 heads, TTT. Other than that, you could have 2 heads. But if you have 2 heads, then that means you have just 1 tail. And all you have to decide is which one of the coins is going to give you a tail. And there's 3 possibilities for that. So there's 3 ways to get 2 heads. There's 1 way to get no heads. The size of the event is 4. And so the probability of this event is 4 out of 8. 4, the size of the event, 8, the size of the sample space, 0.5. And in fact, we could have guessed that to begin with, because if you toss 3 coins, the possibility of getting an even number of heads or an odd number of heads is going to be the same, and both of them are going to be half. So you roll 3 dice. What's the probability of getting exactly 1/6? It's 2 counting problems packaged into one. First, you say, what are all the possibilities? What's the sample space? The answer is use the multiplication principle. 6 choices for the first die, 6 choices for the second die, and 6 choices for the third one. 6 times 6 times 6 is the size of the sample space, the total number of possibilities, what goes in the denominator. What's the size of the event? That means getting 1/6. How are you going to get 1/6? The first thing you do is pick which one of the die are going to give you that 6. You have 3 choices for that. And then for the other ones, for each of them, you have 5 choices because you don't want to use a 6 anymore. So the probability of getting exactly 1/6 is that ratio that comes to about 34.7% or 0.347. If you roll 3 dice, what's the probability of getting 3 6s? Sample space is still 6 times 6 times 6, but the event this time is getting 3 6s, and there's only one way to do that. So the size of the event is 1, and so probability of getting 3 6s is 1 divided by 6 times 6 times 6, so 1 over 216, and that's 0.0046, so less than half of 1%. Our final 2 examples. From among all 5-digit numbers, you randomly pick one, and you want to know what's the probability that you get an odd number and all of its digits are distinct. No 2 digits the same. If you put all 5-digit numbers in a bag and mix them up and just pick one, what's the chances of getting that? What's the sample space? The sample space is all of the outcomes. So that means all 5-digit numbers. How do I find out how many 5-digit numbers I have? It's a 5-digit number. I have 5 spots to put digits in. How many choices do I have for the first spot? 9, because this is a 5-digit number. I can't put a 0, so I have digits 1 through 9. And then regardless of what I do there, I have 10 choices here, 0 through 9, 10 choices, 10 choices, 10 choices. Multiplication principle gives me that I have 90,000 choices. So 90,000 5-digit numbers. But what about the event? What are the number of desirable outcomes? What is the size of the event? So how many 5-digit odd numbers with all distinct digits? You might say that maybe I have 9 choices there. For the next one, I can't use whatever I used before, so I have 8 choices. For the one after that, I have 7 choices. For the one after that, I have 6 choices, but how many choices do I have for the last one? This is a tricky one because this actually does depend on what you do before, because we want it to be odd and I have to use only 1, 3, 5, 7, and 9, but I don't know how many of those I've used before. I know that I've used 4 digits before, but I don't know how many of those odd ones I've chosen. That choice depends on the ones before, so I can't actually use the multiplication principle in this way. We might say, how about if we start from the right and say, here I'm going to use 1, 3, 5, 7, or 9. I've got 5 choices there. I can't use that again because I want distinct digits. So I have 9 choices here, and then 8, and then 7. But then how many there? The problem is that I don't know if I've used 0 or not. Maybe I've used 0 somewhere along the way. Then I've used 3 other digits. And so from the 9 remaining, I've got 6 left. But if I haven't used 0, I've used 4 different digits here, and I only have 5 left. So the number of choices I have here depends on whether or not I use 0 before that, and therefore I can't do it this way either. So the multiplication principle failed us, except if you're slightly clever and do it in the right order. I start with here and say, I've got 1, 3, 5, 7, and 9. Pick one of those, put it there at the ones digit. And I have 5 choices there. But then jump to the left and say, what choices do I have? You could originally use 1 through 9, but not 0. You haven't used 0. 1 through 9, one of them you have used already, and so 8 left. And it doesn't matter which one you use, you still have 8 choices left. Now for the next one, you will also have 8 choices, because originally you had 10, 0 through 9. Now you've used 2 of them, and now you have 8 choices. The one after that, you will have 7 choices, because you've already used 3 and you don't want to repeat. And then 6. And so you multiply those, and that gives you 13, 440. So the probability of picking a 5-digit odd number with distinct digits, there's a 14.93% chance of picking that. The probability is 0.1493 approximately. This was an example of how multiplication principle you can use to find probabilities. It's also an example of how finding finite probabilities with finite sample space is basically counted. You just have to count the total number of outcomes and the desirable outcomes. Our final question, from among all 5-digit numbers, randomly pick one. What's the probability of getting an odd number with exactly one of the digits equal to 4? What's the size of sample space? Same as before. I have 90,000 5-digit numbers. Hasn't changed since the previous slide. But how do I know how many odd numbers do I have with one of its digits equal to 4? I'll start with the right-hand side because I know that has to be 1, 3, 5, 7, or 9 to make this an odd number. So I have 5 choices, and that's never going to be the 4. The 4 is going to be somewhere else. I've got to worry about that 4. I might say maybe that 4 is right at the beginning. If that's there for that slot, I only have one choice, 4. And then what? Here I'm not saying that the digits are distinct, so I can repeat. How many choices do I have for this guy? 9 of them, because originally I would have 10 choices, but I'm not using 4 because I only want 4 once. I have 9 choices there, 9 choices here, 9 choices. And so the total number of possibilities, if 4 is in the left-hand spot, is going to be 3645. But that 4 may not be there. Maybe 4 is here. The reason I had to do this differently is because if 4 is here, the count is going to be different. If 4 is in the second slot from the left, then how many choices do I have for that slot? 1. How many choices do I have for the one before? 8. Why? Because that left-hand most digit cannot be 0, and I don't want to use 4, so I have 8 choices. And then I have 9 choices for this guy and 9 choices for those. The only restriction is that I can't use 4. So 8 times 1 times 9 times 9 times 5. But that 4 could have been in the other 2 spots, and those would all be the same also. So I have to multiply this by 3, and that's 9,720 for a total of 13,365. So probability of getting a 5-digit odd number with just exactly 1 4 from among all 5-digit numbers is 0.1485 or 14.85% chance. This is the end of this lecture. Some version of these topics appears in my book, An Invitation to Combinatorics. Subscribe if you want to see more like them. Thank you, and I will see you at the next lecture.